You ever notice how your brain can learn from a blurry photo or a half-remembered dream? That's not a glitch, it's a design feature. Neural networks do the same, and it's why they're so good at learning from noisy data. Imagine a world where every training example is a little broken. Instead of perfect data, you get messy, incomplete, or even misleading information. That's the real internet, full of noise, but also full of potential. Most people think neural networks need clean data to learn, but the truth is, they thrive on it. The noise acts as a kind of teacher, forcing the network to find patterns in the mess. It's like learning to ride a bike with your eyes closed. The uncertainty helps you build stronger, more adaptable skills. The noise isn't a problem. It's a part of the process. So, next time you see a neural network work its magic, remember, it's not just learning from data. It's learning from the noise. And that's where the real power lies. So what exactly are we talking about? Let's start with the basics. Neural networks are like a system of interconnected nodes, each trying to learn patterns from data. But here's the twist. They don't learn perfectly, they learn with noise. Noise isn't a mistake. It's a feature. Think of it like a signal in a messy environment. The network has to filter out the noise and find the useful patterns, much like how our ears distinguish speech from background chatter. You might think noisy learning is a flaw, but in reality, it's a secret superpower. The randomness in neural networks helps them avoid getting stuck in local minima, letting them explore more of the solution space. This noise acts like a kind of mental exercise for the network, keeping it from overfitting to specific patterns and helping it generalize better to new data. In real-world applications, this noisy learning advantage means models can adapt more quickly to unpredictable environments, like self-driving cars navigating through fog or sudden changes in traffic. It's like having a flexible mind that doesn't rely on perfect information. It thrives in ambiguity and uncertainty, making it a key reason why neural networks are so powerful in today's world. Back in the 1980s, neural networks were just beginning to take shape. Researchers were inspired by the brain structure and tried to mimic it with layers of artificial neurons. These early models were simple and slow, but they laid the foundation for everything that came next. The 1990s brought more data and better computing power, allowing for deeper networks. People started to experiment with more layers and connections, but they still struggled with the problem of overfitting and vanishing gradients. It was a time of promise and frustration. The 2000s marked a turning point. With the rise of big data and GPUs, neural networks started to scale. Researchers discovered that adding noise to training data could actually help models generalize better, which led to the concept of noisy learning. By the mid-2000s, noisy learning became a core part of training deep models. The idea that randomness could improve learning was both counterintuitive and revolutionary. It changed how we think about training, validation, and the role of uncertainty in machine learning. Today, we see noisy learning integrated into everything from self-driving cars to language models. It's not just a technical trick. It's a fundamental shift in how we approach learning, making models more robust, adaptable, and powerful. Imagine you're trying to learn a new song by ear. You hear it once, but it's a little fuzzy. You try to sing it, and it's not perfect. But that's okay, because the noise helps you remember the real song better. Neural networks work like that too. They're like little learners who sometimes hear the signal with some noise. It's not a mistake, it's a way to learn more clearly. This noisy learning helps the network avoid getting stuck on details that don't matter. It lets it learn the real pattern, not just what's in the noise. So, even though it sounds messy, the noise actually helps the neural network learn more accurately. It's like how a messy room can help you find things you've forgotten. In the end, the noise makes the learning stronger. It's not a distraction. It's a helper, like a friend who reminds you of the most important things. Imagine a simple neural network, like a tiny brain made of layers of connected neurons. Each neuron receives inputs, processes them, and passes on a signal. This is the basic structure of any neural network, and it's where learning starts. The input layer is where data enters. Think of it as the eyes and ears of the network. Each neuron here is connected to the next layer, and these connections have weights that the network will adjust as it learns. The hidden layer is like the brain's thinking part. It processes the data from the input layer, applying weights and biases to transform the information. This is where the network begins to learn patterns. The output layer is the final result, the network's answer to the problem it's trying to solve. For example, if it's learning to classify images, the output might be a probability for each class. All these connections in neurons are initialized with random weights, and this is where the noisy part comes in. Randomness helps the network avoid getting stuck in the same patterns and explore different solutions. Once the neural network is initialized with random weights, the learning process begins with a single input example. The network processes this input through its layers, propagating the signal forward, much like a series of interconnected pipes carrying water. As the data moves through each neuron, it is multiplied by the neuron's weight and then passed through an activation function. This function introduces nonlinearity, allowing the network to model complex relationships between inputs and outputs. After the forward pass, the network produces an output that is compared to the actual target value. The difference between the predicted output and the true value is the error, which serves as the signal for the learning process. The network then uses this error to adjust its weights through a process called backpropagation. This involves computing the gradient of the error with respect to each weight and updating the weights in the direction that reduces the error. This process repeats for each input example, and with each iteration, the network learns to minimize the error. The noisy environment, rather than being a hindrance, helps the network generalize better by preventing it from overfitting to specific data points. Now, here's the clever twist. The model doesn't just memorize the data. It learns to generalize by embracing noise as part of the training signal. This means the network becomes more robust, not just to the training data, but to any variation that might appear in the real world. This isn't just about making the model more resilient. It's about teaching it to think in a way that mimics how humans learn. We don't memorize every detail. We adapt and infer, even when the world is messy and uncertain. By allowing some noise in the training process, the model isn't just avoiding overfitting. It's actually becoming better at predicting the future. It's learning to handle ambiguity, which is crucial for tasks like language understanding or image recognition in the wild. This twist is what makes neural networks so powerful in real-world applications. They don't need perfect data. They just need enough to learn from, even when that data is imperfect or noisy. In essence, the model is learning to be flexible, not just accurate. It's not chasing perfection. It's chasing adaptability, which is the real key to intelligence. At the core of this learning advantage is a phenomenon called stochastic gradient descent, where the randomness of the noise actually helps the network escape shallow local minima, pushing it toward more optimal solutions. This randomness isn't just a side effect. It's a deliberate part of the training process, where each update is a step guided by both the data and the noise, creating a dance of discovery and adaptation. In fact, studies have shown that adding controlled noise to the training process can lead to faster convergence and improved generalization, even when the data itself is clean and structured. This isn't just about avoiding mistakes. It's about creating a more robust and flexible model, one that can handle uncertainty in both data and the world it's trying to understand. So while noise might seem like a problem, in the world of neural networks, it's often the key to unlocking deeper learning, better models, and smarter predictions. Imagine a group of kids playing a game of tag in a park. They're all running around, sometimes chasing the wrong person, sometimes getting distracted by the wind or birds. But over time, they start to figure out who's it and who's not, just by moving and reacting. It seems chaotic, even dumb, but their collective movement ends up being surprisingly effective. They don't follow a plan, but they adapt in real time, learning through trial and error without anyone telling them what to do. Neural networks are like these kids. They don't follow a strict rulebook, but through repeated exposure to data, they develop an intuitive understanding of patterns, even when the data is noisy or ambiguous. The noise isn't a flaw. It's the spark that ignites learning. It's what allows the network to explore different possibilities and eventually settle on the most accurate solution, even if it wasn't obvious at first. So, in a way, neural networks are gloriously dumb. They don't need to understand why something works. They just need to learn it through experience. And often, that's enough to get the job done. Before you go, if you enjoyed this, please give it a like and subscribe so you don't miss the next one. And tell us in the comments what you'd like us to make next. We read every single one. Thank you so much for watching. Comment this emoji if you made it to the end.